Hi everyone, I'm Tan Irong, KIB2003 are the members of the groups which will discuss about the real-life mechanics of material cases. Before we enter the introduction, I have a little bit sharing about a disease, which is a cerebral palsy. It is a physical disability which affects a person's ability to move and maintain the balance and the posture. It may also increase the stiffness of the muscle, which causes the person hard to move his limb. Hence, leg pull-down machine is introduced as the rehabilitation device because it is a strength training exercise designed for rehabilitation in the latissimus dorsi muscle. Latissimus dorsi muscle is the muscle which performs the function of downwards rotation and dispersion of the scapulae combined with the adduction and the extension of the shoulder joint. The rehabilitation is processed by pulling the handle of the leg pull-down machine, which is moved via the cable pulleys as opposed to doing pull-downs on the leverage machine. The operation of the leg pull-down machine, including the axial loading, which is also known as the normal stress, which can in the form of compression or extension. Torsional load, the internal shearing stress and shearing strains due to the twisting. Bending and shearing stress on any cross-section of the beam are also occur because these are the effect when the force and the couples acting on the beams. Stress and deformation due to the compound load will also occur in the operation of the leg pull-down machine. Hence, through the learning outcome, we will solve the problem involving a body under the action of axial and torsional loads, solve the problem involving stress in beams, and also evaluate the stress and the deformation of the biomedical device due to the compound load. This is a drawings of leg pull-down machine with the parameters. Thank you.
Hi, my name is Lai Koi Chi, KIB2003. So now I'm going to talk about the LO1. Solve problems involving a body under the action of axial and torsional load. So first, we are going to look at the axial loading. So in this case, we are going to look at this part of the steel wire. So first, the free body diagram of the steel wire is constructed, and this steel wire it will experience a pressure due to the weight of the load. So in this case, the weight of the load is 50 Newton. Next, we are going to calculate the area of section cut using the formula A equals to pi r squared. And then finally, we can calculate the normal stress sigma equals to P over A. So first, we can construct the free body diagram of the steel wire. So it will experience a pressure due to the weight of the load, which is the 50 Newton. So using the parameters given, we can calculate the area of section cut A equals to pi r squared, and we can get the area equals to 7.8540 times 10 to the power of negative 5 meters squared. And then we can calculate the normal stress sigma equals to pressure over area. And then we can get a normal stress which is 636.618 kilopascal. Next, we are looking into the torsional loading. So in this case, we are assuming a man which is holding a bar. And then it rotates the bar. The string wire attached to the bar can be said to be twisted. So first, we can draw the free body diagram of steel wire before twisting and after twisting. Then we can calculate the polar moment of inertia of area J equals to 1 over 2 pi c to the power of 4. And lastly, we can calculate the torque T equals to tau max times J over C. The first figure shows the free body diagram of the steel wire before twisting, and the second diagram shows the free body diagram of the steel wire after twisting. So by observing these two figures, there is a torsional loading which causes the steel wire to twist. So given the parameters, the diameter of steel wire, the radius of steel wire, and the maximum allowable stress, so using these parameters, we can calculate the polar moment of inertia of area. J equals to 1 over 2 pi c to the power of 4. So we can get J equals to 9.8175 times 10 to the power of negative 10 meter to the power of 4. And then we can calculate the torque equals to tau max times J over C. So we can get T equals to 9.8175 Newton meter. So that's all from me. Thank you.
Hi, my name is Teodoru and my matrix number is KIB2003. So today I would like to talk about the methodology and assumptions of LO2 and which is the stress in beam. So first of all, the free body diagram of the beam was constructed, and then the moment of inertia I was calculated by using the equations of I equals to 1 over 4 pi c power of 4. Then we use the formula of total m equals to 0 to calculate the bending moment m. After obtaining the moment of inertia and the bending moment m, the maximum bending stress was calculated by using the equations maximum bending stress equals to mc over I. So next, this is the assumptions for LO2. We assume that the force applied to the both ends of the beam was 35 Newton, you can see here, so that we can find the bending moment of the beam. If the force applied to both ends of the beam is 25 Newton each, then the bending moment is equal to 0. So we need to use a higher force that apply to the both ends so that we can get the bending moment looks like the right side of this free body diagram. So the next assumption was is we assume that the beam that we use is formed by a big cylinder of diameter 10 cm and a height of 10 cm, and another two cylinder beside that have a diameter of 5 cm and the height of 25 cm. Thank you.
Hi everyone, I'm On Jung-won with matrix number KIB2003. Now let's move to the calculation part of stress in beam. This diagram shows the drawing of the cylindrical handle and all the values are well labeled. Here is the free body diagram of the cylindrical handle. Next, the parameters we use are central distance, which is the middle cylindrical support and is equal to 0.05 meter. The weight of load W is equal to 50 Newton and the force applied F is equal to 35 Newton. To calculate the moment of inertia, we substitute all the values into this formula and we will get 4.9087 times 10 power to negative 6 meter power of 4. Next, to calculate the bending moment, we set the moment at this point equal to 0 and we assume it is positive in anti-clockwise direction. When calculating the bending moment, we need to find the shortest distance between the force and the point. So, 50 Newton will move in anti-clockwise direction while 35 Newton will move in clockwise direction. So that is why there is negative sign at 35 Newton. Then the bending moment we get is negative 6 Newton meter. Next, to calculate the bending stress, we substitute the values into this formula and we will get 61.116 kN per meter squared. So at last the handle will bend like this. Next is the methodology for evaluating the stress and deformation of the steel wire. Firstly, the free body diagram of the steel wire is constructed, and the reaction P is calculated by using summation of Fy equals 0. Then the cross-sectional area and stress acting on the cross-sectional area of steel wire is calculated by using the equations A equals pi r squared and sigma equals P over 8. Lastly, after obtaining the stress and cross-sectional area, the deformation of steel wire is calculated by using the equation delta equals PL over 8E and is also equal to sigma L over E. There are two assumptions in this calculation. Young's modulus of steel wire at room temperature is typically between 190 GPa and 215 GPa. Hence, we take the close average Young's modulus of the steel wire, which is 205 GPa. Next, the force exerted by the person on the steel wire is exactly normal to the cross-sectional area of the wire and is equally distributed throughout the sectional area. That's all from me, thank you.
Hi doctor, my name is Eugene, KIB200509. I'll be doing the calculation for LO3, which is the stress and deformation in the steel wire. So, we are interested to find out what are the stress and also deformation in the steel wire, assuming that one end of the steel wire is attached to the top, which is a fixed end, and the bottom is attached to the lower end, which is the free end attached to the handle. So the whole length of the steel wire is 1.00 meter, and the parameters are as shown over here. As you can see here, this is a small section of steel wire where the weight acting over here, the load is 50 Newton. So we have to find out the P acting downwards, which is the force acting on the handle, to calculate the stress and deformation. So by using that Fy equals to 0, we execute this equation and we get P equals to 50 Newton. And to calculate the sectional area of the steel wire, we use AW equals to pi r squared. By using the radius equals to 0.005 meter, we get the cross-sectional area equals to 7.854 times 10 to the power of negative 5 meters squared. So next, we'll be going for the stress to calculate the stress. By using the stress equals to P over AW, the P equals to 50 and the AW equals to 7.854 times 10 to the power of negative 5, we get the stress equals to 636.62 kilopascal. And to calculate the deformation of steel wire, which is the delta equals to PLW over AWE. So we can simplify it as stress over LW over E. By substituting all the value we obtain, we get the deformation at last, which is 3.1054 micrometer. So the conclusion is that we learn how to apply mechanics of material in our real life case, which is the lead pull down machine. By using the theories from mechanical of material, the normal stress and also the torque T of the steel wire are determined, which are 636.618 kilopascal and 9.8175 Newton meter. And besides that, the bending stress in the beam is determined, which is 61.116 kilonewton meter per square. Then lastly, the deformation of a steel wire is determined, which is 3.1054 micrometer. So this will be the reference for our case study, and thank you.